All right, let's go ahead and move on to our next topic. It's a big, meaty topic. And it really comes back to this picture that I like to introduce at the very beginning of an SN2 reaction. So I think we've all seen this kind of SN2 reaction where you use a lone pair to displace something. But buried underneath of that, you should know that when you do SN2 reactions, you add to the backside of things. And why is that? Probably when you first learned about the SN2 reaction, you learned that backside attack occurs, I don't know if you know this, because the sigma star antibonding orbital is biggest on the backside of that carbon-bromine bond. That's why you do backside attack, because the sigma star orbital is huge there, and you want to overlap effectively with the molecular orbitals. And so if you know what the molecular orbitals kind of look like, if you know concepts of phasing and energy, you'll be able to predict which types of arrow pushing are plausible and which types are not. So in this class, we're going to focus on doing representations that look like this. But underneath all of that, I hope you'll have some sort of a sense for how to think about this in terms of spatial interaction of orbitals and the energies of those orbitals when they interact. Because more energetic things are more reactive. Let's go ahead and see if we can figure that out. I'm not sure why that slide got all jacked off there. Okay. Let's go ahead and get into this. What are we going to talk about in this topic? We're going to talk about three things. I'm going to tell you about atomic orbitals. That's pretty simple. S, P, D, F. We're just going to talk about S and P. That's this class. We're organic chemists in this class. And then we're going to talk about hybrid atomic orbitals. Not S and P, but mixes of those. sp3 centered on a single atom. sp singled on a single atom. These are atomic orbitals centered on an atom, but they are hybrids of S and P. Then we're going to talk about molecular orbitals, and this is really the meat of this class. Once you start mixing atomic orbitals, you get bonds. You get enols, you get carbonyls, and so we're going to learn to think about this in detail, because if we can understand the energies of molecular orbitals, we'll be able to predict which arrows are good, curved arrows, and which curved arrows are bad. That's what we want to do. We want to figure out which curved arrows are likely and which curved arrows are not likely. That's the goal of this class. So we'll talk about how to interpret which things are plausible and which are not in terms of molecular orbitals. All right, the first concept that I have to get across to you is orbital phasing. If any of you have taken, I'm not even sure where I remember this, a physical chemistry class, you learn about orbital phasing and Hooke theory and stuff like that. But the sophomore organic chemistry textbooks draw pictures of orbitals. So I'll just remind you that a p orbital like this one right here, so here's a p orbital centered on carbon, here's a p orbital centered on carbon. When those two p orbitals interact, you end up making a bond. Let me go ahead and try to draw out that combination there where you get a bond between these two. So if those two p orbitals interacted, because of this phasing, the top parts are unhashed and the bottom parts are hashed or colored, I'll get a new orbital by the interaction of those like phased orbitals interacting. I'll just draw this hashed in here to show that it's darkened a little bit. And that's a pi bond. So when two p orbitals interact, the phasing tells me I'm going to get a productive bonding combination up on top. That's the pi bond, and on the bottom, and that whole thing together, that kind of hot dog bun, is the pi bond. If I take an amine and I try to add to a carbonyl, those reactions work because there is a productive interaction between these liked phased parts of the orbital. And so if I attack with this orientation, I'm going to end up with a productive bond formation event where I form a bond between the H, that's supposed to be an amine, between H3N and this carbonyl here. So I'll end up with this new bond here with this sigma bonding orbital. I'll make a new bond, a new sigma bond, by combining those two orbitals, the parts of those orbitals that had like phasing. Now I want to contrast this. So why is phasing important? Let's suppose I tried to attack, and this seems just completely ridiculous, let's suppose I tried to attack the middle of this bond right here. That's ridiculous. But why is that ridiculous? Well, it's ridiculous because if I'm adding to an empty orbital like a pi star orbital, right, I'll get a productive bonding interaction right here. Let me try to use a blue pen. I'll get a productive bonding interaction right here, right? That will construct a new bond. So up above, these interactions were constructive. because it involved the interaction of orbital parts that had the same phasing. These interactions here were constructive because I was interacting with like phasing. The bottom part here that I drew in blue is also a constructive interaction. But look what's happening with the nitrogen and the oxygen. See how the phasing is opposite? That's going to lead to a destructive interaction that's energetically destabilizing. I'm not going to get any bond formation if half of my interaction is constructive and the other half is destructive. This is why you don't attack carbonyls from the middle of the double bond. It's not possible to get a productive bonding interaction if you've got orbitals of unlike phasing interacting. This orbital interaction right here, right, between unlike phases is destructive. It raises the energy. It won't happen. That breaks bonds, not makes bonds. So we need to pay attention to phasing as we're walking through these things. That will become more important when we think about paracyclic reactions. Maybe not so much now. Okay. So frequently you're going to be thinking about simple topics like lone pairs. Where do I start my lone pair and what's more realistic? So I've got two different lone pairs that I've drawn for you here. I've got one lone pair on oxygen here, and I've got one lone pair on oxygen here. And there's more lone pairs there I didn't draw. Which one is more reactive? If you have both of those, and that's not an unrealistic situation. If you have a reaction mixture, you have carbonyls, and you have alcohols, where should you start your arrow pushing? I mean, oxygen lone pair is an oxygen lone pair, right? Is that true? No. They're not all the same. We'll talk about this in a little more detail, but what I want to say is if you somehow knew which of those orbitals, and we have specific names for these, but don't worry about the names right now. We'll just call it orbital 1 and orbital 2. If you knew the energies of those orbitals that those lone pairs are sitting in, you could predict which one is going to react faster. And I'm just going to tell you the answer right now. Later at the end of this topic, you'll be able to figure that out. So if I compared the energies of these two lone pair-like orbitals, it's the alcohol sp3 oxygen lone pair that's more reactive. And the formaldehyde carbonyl lone pair, less reactive. If you knew the reactivity of those orbitals, the energies, higher energy orbitals, electrons in higher energy orbitals are more reactive. Higher energy electrons are more reactive. I hope that's intuitive. That's the easy part. If you're a higher energy electron, you're more reactive. That's easy. So if we just had some way to predict which orbitals are higher in energy and which are lower, we've got this whole thing wired. Everything's easy after that. So we got to work on this. We got to figure out how to figure out which orbitals are high in energy and which are low in energy. So we know which pairs of electrons are more reactive and which pairs of orbitals are less reactive. Okay, so let's start reviewing orbitals. Let's talk about atomic orbitals first. So I hope all of you know that there's s orbitals and p orbitals and d orbitals and f orbitals. But everything in this class, we're doing organic chemistry in this class. We're going to do with s and p orbitals. I mean, if you ask me to draw the d orbitals, I can maybe make a half-ass attempt to draw the d orbitals. F orbitals, no way. And there will be cases where those will be useful to you, but in this class, it's just S and P, so that ought to be pretty easy, right? It turns out it's pretty hard. Just with S and P, combinations of S and P, things will start to seem really challenging for us. So we're going to just rationalize everything using S and P orbitals. Now I'm going to start off by telling you something that you kind of already know, but didn't know how to use, and that is telling you that S orbitals, P orbitals, are way higher in energy than S orbitals. P orbitals are way higher in energy. If you're an electron in a p orbital, you are way, way, way more reactive than an electron in an s orbital. Electrons in s orbitals don't want to react with anything. They're close to the nucleus, they're happy. So if I were an electron here, look at that. That electron's not going anywhere. That thing just loves being in that. But if you put an electron up into a p orbital, man, that thing wants to do stuff. Nucleophilic attack, transfer an electron to get it out of that orbital, do stuff. Electrons in higher energy orbitals are more reactive. Now, there is not a periodic table in this classroom. That freaking sucks. Okay, but I'm now going to expect you to memorize the periodic table. Here it is. And hopefully you know H is in row 1. You know, 95% of organic chemistry is carbon, nitrogen, and oxygen. Fluorine, not that common. And I expect you to know the relative positions, and I expect you to know that electronegativity increases in this direction. That's what I expect you to know. And if you had to memorize the electronegativities, you would know that it goes 2, 2.5, 3, 3.5, 4. It's very monotonic because the atom sizes are the same. So electronegativity increases in this direction, and that's what you need to know to figure out the energies of these atomic orbitals. So what happens if I compare a p orbital on carbon with a p orbital on nitrogen? Well, nitrogen has more protons in the nucleus, more positive charges in the nucleus. If you were an electron, you would want to spend your time on nitrogen, not on carbon. That makes sense. You just need to know plus and minus to make sense out of that. So guess what happens to the energies of all the orbitals when you switch from carbon to nitrogen? They all go down. The p orbitals go down in energy, the s orbitals go down in energy, the hybrid orbitals go down in energy. Everything is better for an electron when you go from carbon to nitrogen. All the orbitals decrease in energy. An electron is happier being on a nitrogen-based orbital than on a carbon-based orbital. Okay, so let's see if you can guess what's going to happen if we look at oxygen. So this is carbon over here, this is nitrogen over here. Guess what it's going to look like for oxygen? Anybody want to guess? Lower, yes. Oxygen's more electronegative. So if I drew out the p orbitals for oxygen, they'll be down here. A p orbital on oxygen, there's going to be 3 of those p orbitals. I don't like that. That's not low enough for me to see the difference. Let me make it look more low. You draw it down here. There we go. There's those p orbitals, lower in energy. And the s orbital, even lower in energy. And you get the idea. If we go to fluorine, which is not common, we don't do a lot of fluorine chemistry, but if you did, it would be even lower than the oxygen. So this is a pretty simple idea. If you just know electronegativity and you know these relative orbital energies, you can make some powerful predictions about which orbitals are high in energy, which orbitals are lower in energy, which pairs of electrons are reactive, and then which pairs of electrons are not reactive. That's really our goal. Now, these are all, I'll make the comment here that what I'm drawing out are the 2s and the 2p orbitals. Way down at the bottom, below the screen, down in the basement, there's a 1s orbital that doesn't do anything ever. The electrons in that 1s orbital aren't. I'm not going to keep writing 2p and 2s. I'm just going to write p and s. But there are some orbitals, 1s type orbitals, that are just not engaged in anything. So I'm not going to write 2p and 2s. It just leads to too many numbers. Okay, so pretty simple. There's p orbitals, there's s orbitals. P is higher in energy, more reactive. S is lower in energy. So electrons in s orbitals are lower in energy. So we've kind of made some real headway here with that. Okay, let's start talking about hybrid forms of atomic orbitals. Orbitals centered on individual atoms, but are hybrids of s and p, mixtures of s and p. So here I'm drawing in kind of this diagram here, I'm showing you, I don't know why I drew the 1s orbital. It is so far down. You just ignore that. It's not going to bond with anything. It's not high enough in energy to form any productive bonding interactions. So we've got this 2s and 2p orbitals. So let's suppose I wanted to create hybrids of an s and a p orbital. Let's suppose I made a recipe where my recipe is to take 1 part s and 1 part p and mix them together. If I take 2 orbitals and I mix them together, I'm going to get 2 orbitals out. So if I take a p orbital and an s orbital and mix it together, I'm going to get an sp orbital. That's a hybrid orbital. It's 50% s and it is 50% p. And these are the orbitals that you get when you have linear orientations of molecules. When you have alkynes with linear bond angles, cumulines like allenes, I don't know if you remember those species, isocyanates, those have sp hybridized orbitals. The lone pair that's sticking off the end of a nitrile, like this one right here, exists in an orbital that has a lot of sp character to it. Now if I take 2 of these 2p orbitals, and one s orbital, and I mix them together. So if I take two of these and I mix them with one of the s's, I'm going to end up with 3 orbitals coming out, and they will be sp2 hybridized. Man, that is powerful information. Powerful, powerful information. If I'm mixing 2 parts p and 1 part s, there's more p character. And if there's more p character, it will be higher in energy. More p character. 100% p, you're way higher in energy. What's the percentage of p here in this sp orbital? What's percent p character? Notice how I was so clever to draw it halfway between the s and the p, because it's 50% s, 50% p. But when I switch over here to an sp2, what's the percentage of p character in there? So this one is 50%.
Would it be 75?
No. 67% P, right? It's 2 parts P and 1 part S, so that's 2 out of 3. So that's 66.7% P. Now, sp3, 3 parts P character and 1 part S. What's the percentage of P character there? Now it's 75%. See what's happening to the energies of these orbitals as we mix more and more P character in there? The orbitals are getting higher in energy. If you were a pair of electrons in an sp3 hybridized orbital versus a pair of electrons in an sp orbital, you know which one's going to be more reactive. All you need to know is the P character. You can make a powerful prediction about which kinds of electrons are more reactive. Right? That carbonyl oxygen versus the alcohol oxygen, that's an easy decision if you know how much P character is there. Right? That's powerful. Just knowing that the more P character, P character is more important than the identity of the atom being oxygen or nitrogen. I don't know how you made your way through sophomore or introductory organic chemistry course if you weren't paying attention to P character. It's like the secret sauce that tells you what things are going to be likely and what things are not going to be likely. If you don't know that, you'll have to just memorize everything, and that's really hard. Okay, so P character. Boy, I always pay attention to P character. You don't need to draw those diagrams. You don't even need to assign P character like this, the 50%, 67%, that sort of stuff. So that's very powerful, knowing that P character correlates with reactivity. Let's go ahead and take some examples here. I'm going to draw out some molecules, this time nitrogen molecules, where I compare them. So let me go ahead and draw out a nitrogen-based lone pair that has these kinds of hybridizations. And I'll take some very typical molecules. One common nitrogen-containing base that we use in organic chemistry is triethylamine. We don't use much hydroxide anion in organic chemistry, regardless of what they used back in your second-year organic chemistry course. Sodium hydroxide is not soluble in organic solvents. We use triethylamine is our favorite base that we use in organic chemistry. It's soluble, and that lone pair right there that's sticking off of triethylamine is sp3 hybridized. So that lone pair right there is sp3. 75% P character in that nitrogen atom. Now, another common base that you'll sometimes see us use is pyridine. That's not a good-looking bond there. It's pyridine. And, why should we sometimes use triethylamine and why should we sometimes use pyridine? They look pretty similar. I mean, I assume they're about the same cost, which is very inexpensive. Well, notice the hybridization. That pyridine nitrogen is sp2 hybridized. There's less P character in pyridine than in triethylamine. Pyridine is going to be less reactive. Less reactive as a nucleophile, less reactive as a base, and all we needed to know was the P character there. Now, you'll oftentimes see us using as an organic solvent acetonitrile. We don't ever use this as a base. We use it as a solvent because the lone pairs are almost not reactive. Very few things react with that lone pair. Right? This poor, pathetic lone pair on there is sp hybridized. Now, what does that mean in terms of, I could go back and look up, if I stuck up, there's no scale for basicity. All we have is scales of acidity. So if you stuck a proton on there, let me call this pKa. If I stuck a proton on there, what would the pKa be? I can look these up in a pKa table. I usually use 11 or 10. Usually I use 10 for triethylamine because I'm too dumb to remember the 0.8, and it always does. It's always worked out for me. Actual pK is 10.8. If I look up the pK for pyridine, I usually say 5, but an accurate table will tell you it's 5.2. And if I look up the pK for acetonitrile, boy, you just try sticking a proton on acetonitrile. If you stick a proton on acetonitrile, it's a powerful, powerful acid. It wants to get rid of that proton. It's minus 10. This is a log scale. pKa's are a logarithmic scale. So when you actually look at the relative basicity here, if we wanted to write out the relative basicity, that's what we really care about. pKa's are not intuitive. The relative basicity of the nitrogen lone pair, now we're talking. So I'm just going to assign the pyridine a value of 1. Now, triethylamine has more p character. And just from the pKa's, I can predict the relative basicity of that. It's 100,000 times more basic. That lone pair on triethylamine is 100,000 times more basic than the lone pair on pyridine. So when I use pyridine, I'm using pyridine as a weak base, 100,000 times weaker. And that's due to the p character in there. It's not sterics or anything like that, it's p character. And if I want to put something in with acetonitrile, now we're talking about what is this? This is like 15 orders of magnitude. I'm not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think that's right. And if I'm not right, do you care? You get the idea. 15 orders of magnitude less nucleophilic and less basic because of less p character. So you may think, well, gee, that's not such a big difference. Going from 75% p character to 67 is such a small difference. How could that makes a huge difference? Massive, massive difference. Now, I'm showing you an example for nitrogen. Oxygen atoms are just intrinsically less reactive than so you see less of an effect with oxygen because oxygen is just not very reactive. And so I'll just tell you the numbers for oxygen. If I take an sp2 lone pair here on a carbonyl group versus an sp3 lone pair on, for example, an ether like this, the differences are not as big. In this case, the lone pair on the sp3 is more reactive, but it's only 1,000, not 100,000. So oxygen is just less reactive overall, so it kind of compresses that scale. But this idea that more p character means more reactive is totally valid, right? And that's what you want to know when you look at a reaction, is which lone pairs are more reactive and which lone pairs are less reactive. And you don't need a whole lot here. You've got to be able to assign sp3, sp2, and hybridization. Now, be careful. Be careful here. I've got to remind you, before you assign sp3, sp2, you have to consider resonance. Because if I show you this ester here, methyl acetate, and I say, what's the hybridization of these? You might say, oh, I know that. This is sp2. There's a double bond. That means that's sp2. And these over here are sp3. It's just like, whoa, whoa, whoa. We have to take into account resonance here. There's resonance. Let's go ahead and draw out the resonance here. There's resonance here. Before you assign hybridization, just remember that there's two ways to depict this molecule that are totally valid. One of them will look like this carbonyl, but the other one will look like this switterion species, like that. And now when I draw those electrons out and I ask what's the hybridization, you're going to come up with the completely opposite conclusion. Now in this other resonance depiction, which is just as good, this top oxygen is sp3 and the bottom one is sp2. And so what's the hybridization of these oxygen atoms? Well, it's somewhere in between sp2 and sp3. Is it sp2.5? Maybe. But you're not going to be able to assign hybridization accurately unless somebody tells you something like how much double bond character there is. And then maybe you could start to say, is it more like sp3 or more like sp2? But you wouldn't want to conclude that the carbonyl lone pairs are pure sp2 because that means you're not considering resonance. Okay, so think about resonance before you assign hybridization. Okay, so hybrid atomic orbitals are very powerful. sp3, sp2, pay attention to p character. It is gives you a massive clue about relative chemical reactivity. Now, when you take hybrid atomic orbitals and you start making bonds between atoms, let's move away from just individual atoms and move over to start talking about bonds, molecules, molecular orbitals. Let's go ahead and take a little peek here. What do molecular orbitals really look like? I tried to pick the simplest two organic molecules that I could think of so we could plot out what do these molecular orbitals really look like. And let's go ahead and take a peek here at two species. Over here, I've got cyanide anions, important in prebiotic chemistry. 4 HCNs makes adenine. Right? That's the, and formaldehyde, 5 HCNs make adenine. 5 formaldehydes make ribose. Maybe we could talk about the mechanisms, how you generate those. It's pretty simple organic chemistry. So here is a molecular orbital energy diagram that shows you the energies of the molecular orbitals for cyanide anion. I generated these with a cheap, free computer program that I downloaded from the web. And in a molecular orbital energy diagram, notice that there's this vertical axis that doesn't really mean anything. You know, when you do molecular orbitals, the energies are listed in electron volts. That's not going to mean a single thing to you guys. You know, what's an electron volt good for? You might as well just leave off the units. The units will not help you in any way. So I'm not going to write out units when I talk about the energies of molecular orbitals, because if I give them to you accurately in electron volts, it won't mean anything. All you care about is what's higher, what's lower. That's all that matters when you draw these MO diagrams. You just want to depict some things are higher in energy, some things are lower in energy. If you look at the lowest energy orbital, molecular orbital for a cyanide anion, it's down here at minus 13.7 electron volts. It's way at the bottom. And I couldn't draw it on the same scale, right? Everything here is like 1 or minus 1, and then, you know, minus 13.7 is just like 4 stories down from there. When I look at that orbital, it looks kind of like a ball centered on nitrogen. That's a 1s orbital. It's not participating in any bond. It's just electrons in a 1s orbital just sitting on that nitrogen atom parked there. The next higher energy orbital over here is this orbital that seems to be centered on carbon. That's the 1s orbital on carbon. It didn't really form any bonds to any other atoms. It's just those 2 electrons. Who cares? We're never going to care about those for bonding. But as we go higher, we're starting to see molecular orbitals that look like they're split between atoms in some way. Like this one right here. What's that about? What's that orbital right there? It looks like it's kind of between the nitrogen and carbon. Right? It's this big ball of electron density. That is the sigma bond between the nitrogen and the carbon atom. Right? It kind of looks like those. Sometimes they don't look like anything you can recognize, but that I can recognize as a sigma bond between nitrogen and carbon. It's kind of satisfying, and it's not very reactive. Don't take your arrows and start with sigma bonds when there's other pi bonds there. That's dumb. Like sigma bonds are way lower in energy than pi bonds. We'll get to that later. I see another orbital over here. Actually, let me go to these 2 orbitals up here. These 2 orbitals. Notice how they're degenerate. These 2 orbitals in energy, they're the same energy. What types of bonds do those look like? Yeah, those look like pi bonds. One pi bond is going up and down, the other is going sideways. It's the 2 pi bonds. So there's molecular orbitals for those 2 pi bonds. And now I have these other 2 orbitals here and here, and they're sticking out on the ends of the 2 atoms. And it's kind of weird to see that they're kind of centered on both atoms. This one, to me, looks like it's it's bigger on the nitrogen. This one here is clearly biggest on carbon. Those correspond to those lone pairs. Now, when you draw arrow pushing, the only thing you care about is which pair of electrons is highest in energy. I've only drawn the orbitals for the filled orbitals, and the only one that's highest in energy is the one right here. That orbital right there we call the HOMO, the highest occupied molecular orbital. That's the only one that matters. And it looks like a lone pair that is centered on the carbon. So it makes good sense, if you were to do arrow pushing, to start your arrow from the lone pair that's on the carbon atom. You probably knew that ahead of time. You might have said, oh, that's because of the minus charge, or made up some other thing. But the reason why that carbon lone pair is reactive is because the highest occupied molecular orbital, the pair of electrons that is highest in energy in that molecule, is not the pi bond, not the sigma bond, not the lone pairs on nitrogen. It's the electrons in this orbital right here in that HOMO. That's the most reactive pair of electrons. Now, if you were to use cyanide to attack, let's come over here and look at formaldehyde, and you were to use cyanide to attack formaldehyde, that means we're interested in the unfilled orbitals. If you're adding electrons to an orbital, you're going to put them into an unfilled orbital. So over here for formaldehyde, I've only shown pictures of the unfilled orbitals, and I didn't show all of them. And let's go ahead and start off with where you're adding to, what's the most likely orbital to add electrons to. You want to add electrons to the lowest energy orbital. Electrons want to be in low energy orbitals. So when you add to an unfilled orbital for formaldehyde, you're going to go to the lowest one, and we call this one the LUMO, the lowest unoccupied molecular orbital. Now there's other orbitals here that's like, I don't know, like I don't even know what's going on with these. When I look at these other pictures, like, what is this thing here? And what is it? You may not recognize them. I can kind of make out what's going on there, but they don't look like any picture I've ever drawn. Now, fortunately to me, this picture over here is quite telling. This one tells me that if I add electrons to this LUMO, this is the LUMO right here. That's the lowest unoccupied molecular orbital. It's going to break any bond that is between there. Notice how there's no electron density between the carbon and oxygen. If I add electrons to the LUMO, it's going to break the pi bond because there's empty space in between there. There is no pi bond in this orbital in between the carbon and the oxygen atom. They're avoiding each other. So that's the recipe for breaking the bond. So that would correspond to, if we were to give it a name, a pi star orbital. That means you break the pi bond if you put electrons into that orbital. So molecular orbitals are so complex when you get to bigger molecules, you won't recognize any of them except the HOMO and the LUMO look like pieces of Lewis structures. They will resemble Lewis structures or parts of Lewis structures that you've been adding electrons to. So we can rationalize everything in this class just by paying attention to the HOMO and the LUMO of any molecule when we draw an arrow that starts somewhere and we draw an arrow that ends somewhere. These orbitals, the HOMO and the LUMO, are grouped into a special class. We call these the frontier molecular orbitals. They are at the energy frontier, the highest and the lowest. Now, there's only 3 canonical types of filled orbitals that we're going to start our arrows with in this class, that we're going to do arrow pushing with. There's just 3. All the arrow pushing that you do is going to start with one of these 3 types of filled orbitals. And here they are. There's sigma-type orbitals, right? Sigma-type orbitals are pretty recognizable. They look like electron density in the middle of 2 atoms. So your arrow pushing here, when you draw arrow pushing that looks like this, you're really saying that it's the electron density in a sigma-type orbital that is interacting. When you take pi bonds and you use them as nucleophiles, like this, start your arrow from the middle of the bond, you're just saying it's the electrons in a pi-like orbital that are reacting. And if you take electrons in a lone pair and you make them add to things, you're saying that's the electrons in a non-bonding orbital. We don't call it a lone pair orbital, we call it non-bonding. Those are the 3 types of orbitals. And they correspond, every arrow you draw in this class is going to correspond to one of these types of orbitals reacting. Now, fortunately, if all things are equal, like this all carbon case here, I've shown you cases where it's all carbon, it's not mixtures of carbon and oxygen, we know the relative energies of these orbitals. Sigma orbitals are the lowest in energy, pi orbitals are higher, and non-bonding lone pairs are higher in energy. So all you have to know is which orbital type it is, and you can make a strong guess about which pairs of electrons are more reactive, which pairs of electrons are less reactive. 95% of your arrow pushing in this class, the first arrow, if you have 7 arrows, the first arrow will probably start with a lone pair. They're the most reactive pairs of electrons in your molecules, so it makes sense. And if you don't have a lone pair in any of your molecules, maybe you should think about a pi bond as your next choice for where to start your first arrow. And if there's no lone pairs and no pi bonds, now you're kind of down to sigma bonds. And that's kind of, right? So you need to memorize the relative energies of these orbitals. Yes?
So what priority would, say, the non-bonding orbital would attack? Would it be the p orbital, or would it be the sigma star?
Okay, let's talk about the unfilled orbitals. There's 3 types of filled orbitals. There's also 3 canonical types of unfilled orbitals. So the 3 canonical types of unfilled orbitals, the first one I'm drawing here ought to be recognizable. I've drawn a carbocation, a particular type of carbocation, and we label that as an empty p orbital centered on carbon. And that's the lowest in energy. Now, you already know that carbocations are really, really reactive. You don't need me to tell you that, but here's why they're so reactive. It's not because of the positive charge. It's because the p orbital is low in energy. Boranes are just as reactive as carbocations. It's because they don't have 8 electrons. P orbitals are reactive. The next most reactive place to end your arrows would be pi star. Add to carbonyls. You know, it's not so common to add to CC double bonds, like you can add to enones, but adding to CC double bonds. And the least reactive orbital that you can do would be to break sigma star, SN2 reactions. This predicts that SN2 reactions are going to be the worst reactions in organic chemistry. So if you started your organic chemistry course learning about SN2 reactions, I don't know what that's about. It's like you're doing the worst stuff. But this tells you the relative order. So everything in this class will be some combination of one of these three attacking one of these three, and you need to memorize the energies of these orbitals. Sorry I went over time today.